Welcome to the GAN Talk podcast, brought to you by EPC and hosted by Maurizio Di Paolo Emilio, Marcom Director at EPC. This show brings to life the stories behind GAN technologies and products. In each episode, you'll hear engineers, executives, and academics share insights on the challenges and opportunities shaping the GAN market. Here is your host, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of GAN Talk podcast. Today we will talk our latest news, EPC 1991-128-29-3031, so the latest reference boards. And our special guest is Francesco Musumeci, Application Engineer at EPC. Hi Francesco, welcome aboard. How are you?
I'm good, thank you, Maurizio.
Very good. Thanks a lot for being here. Where are you located, Francesco?
I'm located in Volpiano. I work in an application team in the Marcos Palma team of a motor drive application team.
Very good. So, as I mentioned at the beginning, today we would introduce latest reference boards. As I mentioned, EPC 91-128 and the related ones. They are based on the new family, EPC 231X families. So let's start. Francesco, my first question, what are these evaluation boards? Please introduce these evaluation boards and what kind of applications were they designed for?
Sure. Let's talk about these new 4 evaluation boards. They are three-phase PLC motor drive inverter boards. They have a wide input DC voltage ranging from 10 volt to 80 volt. So the dimensions of the board are 81 per 75 millimeters, including connector. And these boards can be interfaced with the most important controller boards on the market. Thanks to the connector mounted on the boards and our adapter boards that you can find on our website. Also, the 4 board contain all the necessary critical function circuits to support a complete motor drive inverter, for example, including a monolithic power stage with integrated driver, housekeeping power supplies, voltage and temperature sense, current sense, and other protection functions. These applications were designed for e-mobility, also robotics and other application like drone application, for example.
Good, thank you. So, as you mentioned, these platforms are based on ePower Stage ICs. So, what advantages this integration would bring compared to more traditional discrete motor drive approaches?
These platforms, yes, are based on ePower Stage ICs, which integrate multiple power stage functions into a single device. Compared to traditional discrete motor drive solutions, this approach offers several advantages, for example, including reduced PCB dimensions, simplified design, or also a lower component count. This high level of integration also helps optimize electrical performance and additionally, it can reduce the parasitic effect and also simplify thermal management, making the overall system more compact and also better suited for space-constrained application. For example, this is very important for humanoid robotics application or drone applications.
So one of the most interesting aspects of GAN is switching performance, switching feature. So what about, let's analyze a bit better how higher switching frequency would translate into real benefits for motor control, efficiency, acoustic noise reduction. So what about?
Let's start with one of the key advantages of GAN technology, that it is its ability to switch at much higher frequencies than conventional silicon-based solutions, silicon-based device. In motor control applications, higher switching frequencies can improve current regulation, for example, and torque control, thanks to low current ripple on the output current delivered to the motor. This is very important, for example, for a very slow motion operation, such as like a motor control in a humanoid robotics application. From an efficiency standpoint, GaN devices exhibit lower switching losses, and this allow the drive to operate more efficiently, even at elevated frequencies. And also, the very small radius on of a GaN device reduce the conduction losses and reduces also the power losses. This is very important in terms of efficiency, because the low power losses in our devices permit to have low to reduce power losses in overall system. Another important benefit for motor control is the noise reduction. In fact, moving the switching frequency beyond the audible range can reduce acoustic noise of the overall system, and this is particularly important in application such as, for example, humanoid robots, where quiet operation improves both user experience and system acceptance.
Very good. Thank you. So we are introducing, as we mentioned, 4 boards. So EPC 91128, 91129. These are based on the family 23108 and 109, but also the other boards, EPC 91130 and 91131. So they have different current, 18 and 29 ampere RMS, I mean. So let's understand the main differences between these families, how engineers should choose the right platform for their design.
Yeah, as you said, the first main difference is the ICs that single board mount. The EPC 91128 and 29 featuring the EPC 23108 and the EPC 23109 that are 100 volt power stage ICs with 5.7 million of typical Edison. The other 2 boards featuring the EPC 23110 and the EPC 23111 that are also 100 volt, but with 8.7 million of typical Edison. The second difference is about the current that can deliver to the motor for motor drive. The 91128 and the 91129 can deliver up 28 ampere of peak steady state output current and up to 41 ampere of peak maximum output current in pulse mode. The other 2 boards, the 91130 and 91131, can deliver up to 21 ampere of peak steady current and 28.5 ampere of peak maximum output current in pulse mode. Another important difference for these application boards are about the ICs, because the difference is the PWM input on the ICs. The EPC 91129 and 31 mounted ICs with a single PWM input with internal logic circuit to split this in high and low signal. For this reason, these devices also feature an enable function to enable or disable the PWM without switching off the device. The other two boards, the 91128 and 30, have the devices have high and low PWM signal inputs. For this reason, the choice depends on the output current, or the output current required by the application, and depends on the control requirements that the system must meet. But I think these 4 boards provide a good range of options, making it possible to find the most suitable combination in terms of both the current capability and control performance, according to the specific needs of the application.
So motor drives require sensing and protection to be reliable. You mentioned at the start during the first question. So what monitoring and protection features are already integrated on these evaluation boards? Can you say a bit more?
Yeah, these boards equip all the sensing and protection that motor drive must have. Let's start with the inverter is equipped with voltage and current sense for all phases and voltage sense for the DC input. Phase current is measured using all current sensors on each phase. The sensor's current range depends on the boards. For 91128 and 29 is plus minus 50 ampere, I remember. And the EPC 91130 and 91131, the current range is about plus minus 30 ampere. The current sensors are bidirectional, ensuring the full 4-quadrant operation. Also, the main input DC voltage and each phase voltage are measured using a resistor divider network. And another important feature is that the board are equipped with a temperature sensor to monitor the temperature in the center, in the bottom, and in the center of the board. Also, the board include a connector which connects a shock sensor to the motor drive inverter. This is compatible with optical quadrature encoders or Hall effect sensors, and provides a supply voltage for the encoder. It's very important for position control, other motor control for a lot of systems. In terms of protections, the current sensor of the board include an overcurrent detector that triggers if the current measurement exceeds the board overcurrent threshold. The overcurrent signal is active low, and once an overcurrent is triggered, the overcurrent signal will remain low for a short period, and the shutdown signal will be activated on the GAN AC directly on the GAN AC input. Another feature of protection is the overcurrent signal is also sent to the controller to manage the overcurrent errors from also the control side, if you want to control that.
Thank you. So let's talk about my next question, dead time. So when optimizing BLDC performance, this parameter, dead time, becomes critical. So how much flexibility do engineers have in tuning dead time and PWM behavior on these evaluation platforms?
Yeah, depends on the boards, because the EPC 91129 and 31, as I said, mount the ICs with a single PWM input. And for this reason, the time is internally tuned. The time for these devices is in a range of 20-25 nanoseconds. The other two boards, the 91128 and 91130, permit to tune the time from PWM control. But I think we suggest using the time for motor control application lower than 50 nanoseconds to optimize our GAN characteristics.
Thank you. So thank you, Francesco. So this has been very nice conversation, and you have shared a lot of information for these evaluation boards. In conclusion, so for engineers moving from silicon to GaN, from silicon MOSFET to GaN, in this application, motor drives application, what is the single biggest design mistake they should avoid from your perspective?
Yeah, all right. I think that engineers should avoid simply replacing a MOSFET with GaN devices. Because my suggestion is to choose a properly gate driver for GaN and properly optimizing parasitic inductances and the PCB layout. Because it's very important to change the system for to optimize the GaN characteristics. And my advice is for guidance, they can refer to the documentation available on our website, which provides detailed recommendations and application notes for implementing an optimized design to improve the PCB characteristics, the layout characteristics, and optimize the PCB layout and applications with our GaN.
Very nice. Thank you. Our website, epc-co.com. You can find there information, latest press releases about this platform, and the datasheet, the start guide for these platforms. Thank you, Francesco Musumeci, Application Engineering at EPC. Thanks a lot for joining us, and talk soon.
Thank you, Maurizio.